This is the CDFAM podcast with recordings from the CDFAM Computational Design Symposium held in New York City, October 29th to 30th, 2025.
Good afternoon, everyone. I'm Tamijani, co-founder, CEO of Novineer. I'm also a professor of Aerospace Engineering at Embry-Riddle Aeronautical University. I'm very sorry for my voice. I caught cold about a week ago, but then this weather is not very friendly for me. I'm from Florida, so a little bit. So the discussion today is going to be about Novineer's toolpath-based design and simulation. But before that, let me give you an overview of Novineer. So, come on, please. The Novineer technology has been developed from funding that we received from Air Force, NSF, Office of Secretary of Defense, and if I can close something here. And we have shown the fundamental in different journal articles. And so inside Novineer software, we have these three modules: NaviVision, NaviDesign, NaviPath. NaviVision, you provide one or multiple pictures, and it creates an editable CAD file for you. And NaviDesign apply loads, boundary condition, material properties. It provides optimized design that is, again, editable, parametric. And NaviPath simulate and optimize the manufacturing toolpath. The one that is already developed and launched is for FFF FDM, but we are also working on DED version of it. So this is a short demo of how it works. So you take a picture, provide that picture, it create STL, create STP, and then you can go to the next module, apply loads, boundary conditions, and it optimizes the geometry. And then you can go to the next module, and you provide material properties, and it optimizes the manufacturing toolpath. Here are some additional examples for example, NaviVision. And so here you can see you get both STL and STP. This is another proof of concept that we did recently with a defense prime. So our baseline design is a tank wheel hub. The baseline design plus the load were given to us. There were not any manufacturing specifications that were given to us. The goal was show us that it can be lighter than this. And over there you can see the multiple designs that came out of NaviDesign, 20%, 30%, 35% lighter, while having the same performance, meaning the same displacement, same stress distribution, not stress distribution, but failure load. Same failure load as the original baseline design. So today's discussion, however, is about NaviPath. So in FFF, FDM type manufacturing, you often need, if it works, you often need the toolpath. And the reason the toolpath is important is because if you change it, it means you're changing now material direction. Therefore, you're changing the mechanical properties. And as a result, you have a different performance, right? And before Novineer, there was no software that would be able to get the toolpath from Slicer. And then based on those toolpaths, it would say, like, what is the failure load of this part? Or what is the deformation? And or how you should optimize this path to perform better. And so that's why we worked on this. So if there is no software that is doing it, or we're doing it, then how users in industry are using FDM? These are the two ways they do it. Either they experimentally evaluate it, right, which takes days, if not weeks. Building the fixture, printing, testing, right? Or we have heard from several large OEMs during the last 2 years that the way they do it is they consider the weakest property, and then they consider everything to be isotropic, which means if you look at that table, it means a factor of safety of 3, right? Which is like designing dishwasher, not probably designing parts for aerospace, right? So, And the reason is because there was, again, no simulation that would consider the manufacturing path or the 3D printing path. So the question is how FFF can scale if you cannot reliably say how good this part is, right? So that was the reason. To do this, to do any type of design, you of course need simulation, right? And simulation require material properties, but here I'm not going to talk about material characterization. Here the discussion is about simulation, design, and then show you all the validation, verification process that we went through, from printing to testing. And so these are the topics that I'm going to talk about today. The first one is the toolpath-based simulation. So you have the path, how do you do simulation? The second one is now optimizing the toolpath. And the third one is, okay, optimize geometry and toolpath together. So a coupled optimization. I'm not going to talk about geometric optimization when you have anisotropic properties, when the properties are not similar in every direction. Why not? Because, first of all, the result is bad, as you can see here, right? If you fix the path and only optimize the geometry, the result is bad, as you can see here in the last one. And the second reason, it doesn't make sense. Why would you do that? Why would you only optimize the geometry and do not optimize the path? Even if you are talking about conventional composites, why you would not optimize the fiber orientation and only optimize the geometry? I couldn't find the reason, therefore I'm not going to talk about it. So the discussion is going to be about the first three topics. So let's focus on the first one, which is the simulation. So you have all of these filaments inside your part. The way we do it is we break the filament to various sections, right? And as you can see, we have hundreds, sometimes thousands of sections, depending on the part. And then we find the elements that they have. The center of element is between those sections. And then we assign the property from filament to the element for that specific section. For example, in that section A, B, C, D, all of them will have theta 1 orientation because they're all located in that section of the filament. Then we can patch them, several sections, put them together, depending on how close the orientations are. But regardless of what we do, we are going to get at the end hundreds of thousands, sometimes millions of elements. And even if you use parallel processing, even if you use MPI, it's going to take hours to be able to do these simulations. So while this assignment is not difficult, you can use even blind parallel processing to do something like this, but the actual simulation, finite element simulation, is gonna take hours. So the way we took care of it is by using this two-resolution machine learning model. So what happened is, okay, now you assign the property, now you go from fine mesh to coarse mesh, you map the elastic modulus and other properties that you need. You map them to this coarse mesh, you perform finite element on the coarse mesh, you get the result, then you use your machine learning to map it back to fine mesh, right? The same methodology, I heard there were a few talks about like sensitivity, adjoint. The same methodology can be used for sensitivity, because the difficult part of adjoint analysis is that FEA is similar to FEA. FEA takes a lot of time, so what you can do it on very coarse mesh, and then you can map it back to the fine mesh to get accurate, for example, stress derivatives. So that's the way we took care of the high computational cost, and then after that, validation, right? So the first things we did was about the coupon testing, right? So you have this path, you have multiple materials, so it's not about one material. You have still filaments, but filaments related to different materials. And so you have different, therefore, material properties in different sections. And here you can see the computational experimental results are published probably five years ago, yes, 5-6 years ago. And you see 223 megapascal versus 226, so close enough. We did a lot of other testing and validation. I'm going to talk about some of them today, but let's go to a recent one that we did with the Stratasys. So this was a blind experiment we did with the Stratasys. So we were given the 3D printing path in different layers. We were given the geometry, and this is the real environment that the part is being used. And the question was where it's going to fail, at what load it's going to fail, right? And some other simulation software, when we tried the same thing, we had error up to 150%, right? So the question was how accurate this can model this problem. So these are the two load cases that were given to us. The first load case is, you can see the load is applied In both load cases, the load are applied vertically, but the part is in different orientation. One of them, of course, is weaker than the other one. And then, so here you can see the tool path, and then the other data are coming from like the tip, and other things are coming from the GrabCAD, and this is the actual experimental testing. And here you can see where the part broke and where the simulation is saying the part is going to break. That was for the stronger one, and this is the weaker one. And again, here you can see here the deformation, and then afterwards you will see the comparison between the failure loads between the two. So again, for this one, you see it's saying it's going to fail here. So here you see the failure loads for these two cases. And for load case 2, you see the difference is about 5%. So great, right? For the load case 1, you see the difference is about 18%. It's not bad still for simulation versus experiment, but it's not great. So what's the reason? The reason is because the part was loaded, unloaded many times. So the reason is fatigue, something we didn't consider in our simulation, right? Okay, good. Now you have a validated simulation, toolpath-based simulation. Now the next step is I want to optimize it. I want to optimize the toolpath, right? How should I do it? So in 2000, this is showing how we get the path and then a little bit more information about the simulation. Let's move on to this. So back in 2017-18, we published an article about what is load path, because in industry, they talk about load path, like something that is known, but we couldn't find any definition for that, like what is exact load path. So we offered this definition. A structural load flow is the component of internal load that is from or to where the boundary condition is or where the load is applied. Okay, so based on that, we came up with this hypothesis that in every structure, there must exist a load function. That if you look at the contours of that load function, the difference between the amount of function value between the two contours must equal the amount of load that is passing through that function, right? And we mathematically proved this, and we showed how this works. So if you have the stress distribution inside your part, you can take derivatives, and then you can get those functions, and then you can draw them. Okay, great. Now you have load path. Probably the best thing you can do is put exactly the filament on those load paths, because they will make sure the load is transferred from point of application to point of support, as you will see in some examples. But there was a problem. The problem is that the load path doesn't have to be in one layer, right? And here we are talking about layer by layer additive manufacturing. The load path, depending on where you're applying the load, can be a curve, right? So if you have a kind of a robotic printer, right, then it's possible, as you can see for this case, it's possible to go from point of application, the two top holes, to point of support, which is the two bottom holes. But then if you're using layer by layer manufacturing, 2.5D type manufacturing, then there is no way you can do that. The only thing possible you can do is try to connect the path in different layers, as I will show you later, right? So then there are different scenarios depending on what manufacturing method you are using. The first step is to analyze the part to find out the 3D distribution of the stress inside the part. Based on that, get the load path. But then after that, the manufacturing specifications become important. Based on manufacturing specifications, either you will have this curved layer or you will have a straight layers in different dimensions. So here are three ways you can do it. The conventional way, which is the first one, right? This is the conventional way. You can find it in any slicer. Cura, this is the way you do it, right? So there are two conventional ways. The first one is unidirectional, right? Whatever angle, but unidirectional. The second, in different layer, you can have different direction, but in each layer, unidirectional. The second way is boundary offset. So you can see both of them here in this case, boundary offset and unidirectional. Now, the other two are from NaviPath. So the first one, if you design different path in different layers, but still you can see you are going from point of application to point of support in each layer. So for the first layer, you go to the first point of support. In the second layer, you go to the second point of support. If the load and the support are on the same layer, you are very fortunate. That's the best case for layer-by-layer additive manufacturing. Then you can define this unified toolpath, which is going to be much better than changing it in different layers, as you will see. So how much am I going to gain from doing this? 60% improvement in stiffness. Don't change the geometry, just change the path. This is what conventional slicers can do. And these are the two that we have done, optimizing the toolpath. That's huge, right? And you can also look at the failure analysis, look at the failure index, where the weakest part is, how you can make it stronger, and all of that. Okay, great. You optimize the toolpath, and sometimes you don't want to go further, because if you change the geometry, then there is going to be design review, design committees, all of that, right? But if you have the luxury to change the geometry and toolpath together, that's where this one will help, right? So the best way to do the change in geometry is implicit. And the reason is because it makes sure that the part is not going to break during the optimization iteration. And implicit means level set, right? So you define a function. If you cut it at 0, you get the boundary of the part. And then while the math seems difficult, it's actually really easy. You use the Hamilton-Jacobi, move it up and down using the velocity until you get to the right shape, right? But the important thing is that there are two parts here now. The first part is the sensitivity with respect to the shape, and the second part, G2, is the sensitivity with respect to the path. And that's why it is a coupled optimization, not just topology or shape optimization. So the question is, again, how much would I gain? You already showed 60%. If I do both of them, how much am I gain? So here is a result, for example, that is again published, and you can see that 90% improvement in stiffness if you do both geometry and topology optimization. And at some point we had this hypothesis that maybe doing topology optimization is not good because it sometimes increases the singularity in the direction. Direction suddenly changes because of all these different members that you have. Maybe shape optimization is better than topology optimization. We compared them. No, the hypothesis was wrong. Actually, topology is better, right, than shape optimization. And at least with a couple of tests that we did, we found out that the topology optimization is much better. Here you can see the result for the two, the topology and the shape optimization. Right? And sometimes there is a discussion whether I should do a stiffness-based or a strength-based optimization. Strength-based is, of course, much more difficult, but much more valuable. Here is an example. Right? So this one is stiffness-based, that one is a strength-based. You see while the stiffness in both designs are kind of similar, 103, 96, the failure load is completely different, right? 42 versus 96. So 2 times better failure load if you do strength-based optimization. So what is the next step for us? Building API, right? API with different slicers, different 3D printing OEMs. Why? Because if we do that, then you don't have to upload the model or upload the toolpath or select material. None of that. All of that can be transferred from a slicer to the software. If you don't need to optimize the toolpath, great. The toolpath is what you selected originally in the slicer, and you can just do simulation to see how good the part is. If you want to change it, you can do the optimization inside our software, and you can compare it with the original solution. Thank you very much for your time.
To see the full recording of this and previous presentations, as well as information about future CDFAM events, visit cdfam.com.